Hello everyone. Today my team Giska, Hanif, Praveen and myself Esther will be presenting to you on our group assignment 1. Here are the contents we will be sharing today, starting with Singapore URA control plans, which are our site studies, and next will be the urban environment analysis, where we use FOMA to analyze the existing site condition. Lastly, will be our proposal on URA Green and Livable City, where we compare the before and after of the analysis and why we proposed it. Starting off URA's control plans, we have the site that we are focusing on is at Raffles City Mall. This URA master plan shows the typology around the proposed site, and its plot ratio is 9.9. And the MK lot number is given stated below here, and it shows the map on the most left side shows the active regenerative users around the site surroundings. The images taken are located at the underground level, connected to CityLink, where the UPL is located, and the active generating users are located at the first story.
Moving on to the building form and massing, the ground floor of the building facing Main Street should make a strong visual impact while fitting well with nearby landmarks. It must preserve important sightlines like those from Bras Basah and Stamford Road and create a welcoming pedestrian-friendly environment. While expressing its own identity, it should still complement the surrounding architecture to enhance both the streetscape and skyline. Here are some of the images taken on site. Building heights are carefully planned to create a layered and balanced skyline. Taller buildings like Raffles City are positioned further away from key landmarks, while lower buildings are placed near open spaces, heritage sites, or important public landmarks such as the War Memorial and CityLink Mall to maintain a human-scale environment. These height differences helps preserve important views and ensure visual comfort. Additionally, building height is controlled by both urban planning guidelines and technical constraints such as airspace restriction and safety regulation. So the building edge defines how a development interacts with the street and surrounding public spaces. For this site, urban design guidelines require a minimum 4-story building edge along the key frontages to create a strong and continuous street wall. This helps frame the public realm, enhancing the pedestrian experience and maintaining the civic district of the area. The 3D diagram further illustrates how the building frontage is distributed, 60% along one street edge and 40% along another, allowing flexibility in design while ensuring the building addresses and activates both frontages effectively.
As part of key urban planning guidelines, major developments such as Raffles City must include open or covered spaces that are easy to see into the move through, ensuring clear visibility and accessibility. These spaces must remain open to the public at all times, without gates or barriers, and connect seamlessly to surrounding ground level walkways. They should also integrate with wider pedestrian networks linking to underground passages like CityLink or elevated walkways such as overhead bridges, promoting continuous barrier-free movement throughout the city. For greenery replacement and landscaping, all new developments are required to include landscaping features such as greenery, sky terraces, and roof gardens like on level 7 of Fairmount Hotel, the drop-off point near Coffee Bean and Tea Leaves, to enhance urban greenery, reduce heat, and support sustainability. Night lighting, it enhances the beauty of building by illuminating walls, roofs, and pedestrian walkways, contributing to the vibrant city skyline. At Raffles City, red lighting highlights classic elements, while blue tone reflects a more contemporary urban character.
Next is the pedestrian network. The developments within the downtown core area are required to provide covered walkways at the first story. These covered walkways serve as public amenities to the public and must be kept free of obstruction at all times. Additionally, the area occupied by these walkways are exempted from GFA computation. Followed by servicing vehicular access and car parks. To maintain a clean and pedestrian-friendly streetscape, all service areas must be in the basement and fully concealed. Electrical substations are allowed at ground level but cannot face main roads or public spaces. Vehicle access points must be minimal and built into the building to reduce traffic impact. Due to the CBD location, basement car parks are mandatory. Lastly, the last planning parameter, which is works within the road reserves. This includes upgrading roadside pavements during new or major works, providing sheltered links to nearby bus stops or taxi stands, and also using a standardized Polo Plus Signum streetlights.
Moving on to the FOMA analysis. Our sun hours analysis for the site near Raffles City shows that it received a strong amount of sunlight overall. About 98% of the ground gets at least 3 hours of direct sun, meaning there's very little overshadowing. Most of the site, around 74%, gets between 4 to 7 hours of sunlight, which is great for creating comfortable, naturally lit public spaces. Only a small portion, about 2%, receives less than 3 hours of sunlight, mostly in areas blocked by the buildings themselves. The southern and southeastern parts of the site, especially those facing Beach Road, enjoy the most consistent sunlight due to their good orientation, making these areas ideal for greenery, outdoor activities, and energy-efficient design. The sun analysis on the building's form shows that sunlight is fairly well distributed across the surfaces. Around 25% of the building gets over 9 hours of sunlight, which makes these areas perfect for things like solar panels or rooftop gardens. Another 20% of the surface receives 6 to 7 hours of sun, and about 13% gets 5 to 6 hours, so there's a good portion of facade that benefits from strong sunlight. These areas are great for bringing in natural light and applying passive solar design strategies. Over 58% of the building gets more than 5 hours of sun each day, showing good potential for solar energy use and natural heating. On the other hand, around 15% of the building receives less sunlight, so those areas might need extra artificial lighting or better insulation to stay comfortable. In general, the design strikes a good balance, allowing us to take advantage of sunlit areas while also planning for the parts that are more shaded.
The wind comfort analysis conducted using FORMA shows that the site provides a high level of comfort for people at the ground level. About 93% of the area is suitable for standing, which is ideal for public spaces and outdoor waiting areas. An additional 7% actually supports strolling comfort, making it pleasant for pedestrian movement. These results indicate that the site wind conditions are generally favorable for human activities, supporting comfortable and active street level experiences throughout most of the development. At roof level, the wind comfort analysis shows that the conditions are generally suitable for outdoor activities. 55% of the roof areas are comfortable for sitting or standing, particularly along the swimming pool area at Raffles City, making it ideal for recreational use. Meanwhile, 44% of the area is suited for strolling, which is appropriate for spaces like the tennis court. Overall, the roof level wind environment falls within an acceptable comfort range, supporting active use of the rooftop amenities and enhancing the quality of outdoor spaces at the elevated level. The wind analysis revealed that the prevailing wind direction on site comes mainly from the north, with wind channeling more effectively between the taller towers at ground level. At the ground level, 95% of the wind direction flows through the site, especially around the taller buildings, where darker blue areas indicate higher wind speed. These speed ranging from 3 to 5 meters per second are suitable for outdoor comfort and enables opportunities for passive ventilation. At the roof level, about 68% of the wind flows across, but with lower intensity, making it less impactful than at the ground. This understanding supports better design decision for natural ventilation and placement of outdoor amenities.
Next, this analysis looks at the daylight potential of the proposed building, comparing it between good daylight access and low daylight access. On the left, we have areas highlighted in teal, which represents good daylight access. These parts receive a high daylight score of between 27 to 37, covering approximately 93% of the building surface. These scores are achieved thanks to vertical massing, which minimizes ground coverage and allows more light to penetrate the facade. Additionally, the building's east-west orientation helps to capture both morning and afternoon sunlight. On the right side, the blue highlighted zones indicate low daylight access. These areas score below 27 and make up only 7% of the building surface. They are mostly located at the southwest orientation, where daylight is obstructed due to adjacent tall buildings, shading devices, or deep overhangs. As a result, these zones may require supplementary artificial lighting. In conclusion, our daylight analysis shows a strong overall performance, with over 90% of the building surfaces receiving sufficient natural light. However, we also identified a few underperforming areas, mainly located at the building base and in recessed zones. These areas are affected by self-shading and surrounding urban geometry, which limits daylight penetration. Hence, the design not only enhances energy efficiency, but also improves occupant comfort by thoughtfully maximizing daylight exposure.
This microclimate analysis of Raffles City shows how building form and layout affects local weather conditions. Areas in darker orange indicate higher temperatures, typically found where tall buildings are tightly packed. These structures block wind flow and traps heat, creating hotter and less comfortable environments. By analyzing data like wind direction, solar radiation, and thermal comfort levels, designers can better understand how sunlight and air movement interact with the urban form, helping to create more sustainable, climate-responsive cities. To improve urban comfort and reduce heat stress, designers can apply cooling strategies based on the microclimate data. This includes changing building orientation, adding shading devices, planting trees, and integrating green roofs or rooftop gardens, like those here seen in Raffles City. Expanding greenery, incorporating water elements, and designing well-ventilated corridors can significantly enhance airflow and comfort. These strategies create healthier, more livable environment, especially during peak heat hours. So next, we'll be going through our proposed urban ideas for URA green and livable city. So here is influenced by the analysis of our current existing site. This is our overall proposed idea on the urban level of the Raffles City.
From the wind analysis, we found that the tall buildings on the site tend to block the natural wind flow, which leads to areas where the air doesn't move much and creates pressure spots around the podium level. To help with this, sky terraces have been added at certain mid-levels of the towers. These open spaces allow air to pass through the building, which helps reduce wind build-up at the ground level and support natural ventilation. Sky terraces also contribute to a greener and more livable environment. They provide shaded areas for people to gather improved thermal comfort and encourage biodiversity with greenery at height. On top of that, they help connect different levels of the building, both visually and physically, creating an open and connected vertical space. This approach also supports sustainability by reducing how much we rely on mechanical cooling systems. The elevated link bridges connecting the hotel and office towers help improve pedestrian flow on the upper levels, which reduce crowding on the ground. At the same time, these bridges act as green connectors by incorporating plants and greenery, supporting the idea of biophilic design. By placing the bridges strategically, they also help manage wind flow between the towers, reducing wind pressure and improving ventilation as shown in the wind analysis. Adding plants and shaded areas on the bridges creates more comfortable zones where people can rest and interact, while also supporting diversity at higher levels of the building. Overall, these link bridges not only enhance the city's skyline with visual openness, but also support Singapore's goal of building a green and livable city by improving comfort, promoting sustainability, and enriching the user experience.
The integration of green walls is guided by a sun hour simulation, which shows that 98% of the ground received over 3 hours of direct sunlight daily, indicating excellent solar access. A before and after sun analysis was conducted to assess how the meshing changes affect solar exposure. The before scenario shows intense sunlight focus on certain areas, while the after scenario with adjusted building heights and form demonstrates a more balanced sunlight distribution across podiums and facades. To optimize sustainability and building performance, green walls are strategically integrated into zones with high sun exposure. These green walls actually help to enhance the urban biodiversity, reduce the urban heat island effect, and improve air quality. Positioned along highly exposed elevation and podium edges, they contribute to a more breathable, visually engaging streetscape while supporting ecological connectivity and providing thermal insulation for the building envelope. Next, on the solar panel, a before and after sun analysis shows how the proposed meshing adjustment allows for better solar access across key rooftop areas. In response, solar panels are strategically placed on the rooftop that receive the most sunlight. This integration not only enhances energy efficiency and support renewable energy goals, but also contributes to a long-term environmentally sustainability at both the building and urban scale.
Next, this proposed streetscape reimagines the existing road network by narrowing vehicular lanes to prioritize pedestrian movement. This was achieved by implementing water features along both sides of the road. On top of that, we have introduced enhanced tree planting and soft landscaping to improve thermal comfort, stormwater management, and air quality. These green elements not only support biodiversity, but also allow better airflow at ground level, helping to cool the urban environment. Overall, these design strategies foster a more comfortable and inviting public space for pedestrians, cyclists, and the wider community, encouraging interaction and healthier mobility patterns. In conclusion, from our environmental analysis study, we reimagine Raffles City as a future-ready, green, and livable urban hub. By integrating features like sky terraces, green link bridges, green walls, and solar panels, the design promotes climate responsiveness and urban resilience. Pedestrian-first streetscape supports active mobility and connectivity, while generous landscaping enhances comfort and biodiversity at the ground level. This design work together to optimize both building performance and user experience while contributing to a more sustainable, walkable, and ecologically rich cityscape. Ultimately, this proposal supports Singapore's vision for a green and livable city, not just through technology, but through thoughtful and inclusive urban design planning. That's all for our presentation. Thank you.